All right, we are going to continue talking about scikit-learn pipelines. Within scikit-learn, we have access to a number of useful pre-processing classes. So, for example, standard scalar is something that scikit-learn provides and we can use in a pipeline. Simple imputer is something that scikit-learn provides and we can also use in a pipeline. There's a nifty one called select percentile, which will allow you to determine what is the optimal percentage of features to keep. Is it 10%, 51%, 88%? And that's based on a univariate calculation of the relationship between a feature and the target. And again, this is something that we can tune if we want to determine what is the optimal percentage of features to keep. Now, oftentimes there can be an interaction between the hyperparameters of our pre-processing and the hyperparameters of our modeling. So you want to try to optimize those together as much as possible and figure out what combinations actually produce the best empirical results. Now, what I'm showing you here is actually a little bit of a preview of an upcoming video on something called a column transformer, but this is a good example to where we can see all the different types of pre-processing we can stuff in a scikit-learn pipeline, including these off-the-shelf classes. Now, there could be a case where we want to write our own custom class to go into a scikit-learn pipeline. Previously, we saw the function transformer, which allows us to take kind of a plain Python function and then apply that in a scikit-learn pipeline. That is certainly useful, however, it can be limiting. If we write a class on our own, it gives us the ability to have a little bit more flexibility and then also be able to tune hyperparameters. So let me show you exactly what I'm talking about. One class that I've written is called the centrality encoder, and you're welcome to look at the code yourself. Basically, what this does is this will do some basic network analysis to replace a category level, in this case, teacher and advisor, with that entity's eigenvector centrality. So our class has to fit a bit of a template. We have to inherit from base estimator and transformer mixin, which are from the scikit-learn base library. Fit is where we actually do the mathematics. So in this case, we are coming up with the eigenvector centrality and then adding that to a mapping dictionary. And then in transform, that's where we actually apply what we have learned in fit. So if you want to know more about scikit-learn fit and transform, you can look at the documentation. But basically what we are doing is we are creating a class that mimics how scikit-learn's off-the-shelf classes work. And it kind of follows this general template here. So here's what happens. We create a very simple data frame that deals with academics. We instantiate our centrality encoder. We can run fit and transform in one single call. And then after that point, we're just going to print out a bunch of output to see what happens. So just as a quick overview before we actually print everything out is we will look at the mapping dictionary, which is an attribute in this class. Then we will pickle that encoder, read it back in, see what that mapping dictionary looks like, and then using that encoder that we've written to disk as a pickle file and then read back into memory and deserialized, we will reapply that encoder as well to see what happens. So let's go ahead and run this. And we can see there's a lot of output. So let me make this a little bit bigger here. So we can see that we have a very simple data frame, and that's what we print out here. And then we can also see that, okay, actually that's what we print out here. I need to make sure I point to the right location on this. So that's what we print out on line 64. And then on line 66, we actually apply the encoder by fitting and transforming it. And then here's the resulting data set. So we can see that we no longer have A, B, C, D whatever strings that we have here, we now have actual float numbers, and those represent the eigenvector centrality of those strings. So the eigenvector centrality of A, which is a person that can be a teacher and or advisor, their centrality is 0.571654. So if we scroll down, before we actually pickled this encoder, we printed out what the mapping dictionary was. So again, this is what just gets applied in transform. So we can see that we print that out, we pickle it, and then we immediately read it back in. So this would be a mimic of what we would do in a production environment. We would train our encoder on our training data, and then in production, we would read in that file and apply it. And we can see that the mapping dictionary is the same. So by pickling this encoder, we have also pickled the attributes of this class. So we can persist the state of this mapping dictionary. And then what do? I create a very simple data set that, again, this might be something we get in production. I print that out here. That's just 2 rows. And then I apply the encoder that we have read in as a pickle file. And we can see that, okay, teacher A, person A, advisor A, whatever role this person has, this has an eigenvector centrality of 0.5716, goes on for several more digits after that point. And then again, if we remember that A here represents this location in the data frame here, it's the same number. So we can see that we were able to learn those parameters on our training data, serialize that, and then remember those parameters when we were applying something in a mock test environment. So that's one benefit of using a class that we write ourselves, is that we can kind of apply this fit transform methodology to give us parameters that persist across different runs of the model, and we can serialize that and deserialize that, which will definitely help us run production level models and pre-processing that match exactly what happened when we were training our model. All right, so I also mentioned that with this, we could tune the hyperparameters of these classes. So again, sometimes with pre-processing, we don't know exactly the best way to pre-process our data. And how do we want to actually determine what is the best pre-processing? Well, in an ideal world, we want to test that empirically, and we want to test how that pre-processing interacts with other pre-processing steps and with the actual model itself. So an XGBoost or a light GBM model or something else. So let's see what that looks like. Again, I just generate a very simple data set here, a target that we're trying to predict. So this is just a class of 0 and 1, a price, a channel, a message, and we can see that in channel and message, these are string columns, and some of these choices, again, this is just randomly generated, but some of these choices will have pretty small probabilities of being chosen. So then the question becomes, okay, do we actually want to collapse some of these sparse categories into one? And so that might be something that we actually want to test. And what should the cutoff for that be? Should it be anything that occurs under 1% of the time, under 5%, under 10%? We can theorize, but again, what we actually want to do in practice is empirically test what pre-processing works best. So in a real production model, we would have this step with probably additional things in our pipeline, as we showed in, what script was that? And that was in column transformer. So this is more of what we would see with a real model, but we're just going to do something a little bit stripped down here in custom transformer. So again, just generate some random data here, create our train test split. In an earlier video, we talked about hyperopt. So we're setting up our hyperparameter optimization with hyperopt here. Scrolling down to the bottom, we can see that we're calling our function. And then this is our pipeline. So our first call is to a class called combined category levels. After that point, we need to do one hot encoding so that we're not modeling strings, because machine learning models cannot understand strings. A library called cat boost, you can actually just pass in the raw strings and it handles the encoding for you. But in most cases, you actually have to do something to convert strings into an embedding space or dummy variables. So that's what one hot encoding does, is dummy variables, and then we apply our model. So you've kind of seen this parlance before with pipelines. But one thing that I want to point out is, all right, in addition to tuning model parameters, we are tuning the sparsity cutoff in combined category levels. So this is just passing in a uniform distribution to say, what should the sparsity cutoff be for collapsing rare strings, if you will? Should it be basically turned off at 0? And we're going to go all the way up to 5%. So this would say that if any category level occurs under 5% of the time, then let's collapse that into a sparse category. So let me actually just briefly show you the combined category levels class. We can see that it does have a default sparsity cutoff of basically 0. So you could just apply this directly if you wanted to. You wouldn't have to tune the hyperparameters. But again, what we want to do is actually figure out what's the best sparsity cutoff. We can see that we have a fit and a transform. And again, mapping dictionary is what we are actually wanting to learn. So this is what we quote unquote learn in the fit, is basically if we were to apply a certain sparsity cutoff, how would that be mapped in a production or transforming environment, if you will. So again, I'm not going to get too terribly much into detail on this, but you can kind of look at the fit transform here if you want. So without further ado, let's train this. And we can see that, okay, we have produced our CSV of cross-validation scores. We've also produced our model pickle file. In this case, this would be a pipeline that would include all of these steps. And then here at the end, I just print out the pipeline so you can see what happens. So combined category levels, it found the optimal sparsity cutoff to be 2%. So any category that occurred less than 2% of the time, it actually found that it was best to combine that into a category that's just sparse combined, basically. So this is just random data. Again, so if I run this one more time, we're probably going to see different results because I'm not setting the random seed. Again, I misread this. This basically turned it off by saying that anything was less than 0.2% would be the best sparsity cutoff. Again, this is changing because I'm randomly generating new data each time. Let's run this one more time. We can see that now it's about 4%. So again, the whole idea here is not necessarily the specific results, but the fact that we have come up with our own class that has a hyperparameter called sparsity cutoff. And then we are, whenever we're doing our optimization routine, in addition to figuring out what's the best max depth for the random forest, what's the best max features, we are figuring out what is the best sparsity cutoff based on our class. So we could also do this for a number of different types of pre-processing, but I wanted to introduce the idea that you can actually tune the parameters of your pre-processing if you write these types of custom classes, and this is something that can be extremely powerful.